Hello and welcome back to the shocking conclusion to L4.3. We were talking about how if the corresponding angles of a shape are congruent, are the same, so matchy-matchy angles the same, and corresponding sides of the shape are proportional, two shapes rather, because we're comparing two things, then they're similar. This is like the old school definition of similar. Angles same, corresponding sides, pairs of sides, proportional. But our definition, two figures are similar if the second can be obtained from the first by a sequence of rotations, reflections, translations, and dilations, can show that this definition is dependable. It'll make it make sense. Let's make it make sense. So the corresponding angles of triangle ABC and triangle RST are congruent. So here's how I understand this. I better see two triangles in a second, because they're talking about two different triangles here. They've named them. They better show them. And corresponding angles, so the matching angle pairs are the same, are congruent. And the corresponding sides, so matching pairs of sides, are proportional by scale factor k. So up until this point in this unit, we've been calling scale factor SF, a number scale factor. But mathematicians don't like to write two letters for a variable. They like to write one. We do write two letters to signify distances in geometric figures. But the scale factor is not the distance between SF. It's not like this. So now we're going to try to switch to K. Oops, sorry. It's not like this. So now we're going to try to switch to K. Does it make sense? Well, if we erase some of these, okay. If we move A to R and then rotate it a little, it'll look like this. This triangle can go here. Okay, see? Do you believe I moved it over there? I translated it, rotated it. No reflection necessary. And now if I scale up all these sides by the k factor, it looks like k is like 1.5-ish. This will grow out to here, this one will grow out to here, and this one will grow to this size. Perfect. Alright, will this work for more than just triangles? Yeah. Let's extend me and Mason's justification that scaled drawings of triangles are similar to show that scaled drawings of quadrilaterals are also similar. So how do you get to be a scaled drawing? Well, you have to have scaled up sides. And all the angles stay the same. And here they are. Does this work with the same logic? Yeah, let's take this corner B, slide it over here. And then I'm not doing this with patty paper because by now we're supposed to be able to do this in our heads.
Mr. Abden.
Okay, wow, lots of interruptions today. Okay, there's the little guy. I moved him over there. Now so this needs to get yay bigger, k bigger, literally. And this needs, look how that like proportionally matches. Those are the same amount bigger than each other. And that is the same amount as this side scaling up and the same. Now this side is the longest, but notice how it ends up the longest. It also grows the mostest because it's already bigger. It's already the biggest, so when you scale things up by the same percent or the same amount, the biggest ones get the biggest. And it does. Okay, so it works. If everything's scaled correctly and all the angles stay matching, then we are similar. All right. Two polygons are similar if all corresponding angles are congruent and all corresponding. That's what I've been trying to say. This book won't listen to me. How does this definition help you fix the error in Mason's thinking about conjecture 1? Something about the sides not proportional. That was the rectangle one. Where you had a squarish looking rectangle and a not squarish looking rectangle. And he was saying, well, the angles all match, and if you move it over there and grow it, yeah, but it doesn't grow right. How does this definition help confirm? Me is thinking about conjecture 2. I probably talked about it a bunch at the time, so write whatever you want here. How might this definition help you think about the other 3 conjectures? All isosceles triangles are similar. This was false. Can't guarantee, that's guarantee, spelled funny, huh? That angles match from iso to iso. From isosceles, I can't spell isosceles. Scullies. There we go. Isosceles to isosceles. Oh my gosh. Same thing with rhombuses. Now squares you can guarantee, and actually squares work. Haha, this works. Angles always 90, so they're congruent. Sides always 1-to-1 ratio. Bam. So all sides scale up the same. From our work with rectangles, it is obvious that knowing that all rectangles have 4 right angles, so A, is not enough to claim that all rectangles are similar. That's right, it's not enough to claim because we don't know anything about the sides. We got to know about the sides. You can't just know about the angles. What about triangles? Now, triangles are special. This was my whole rant last time about how everything in a triangle is connected. A triangle is special because if you try to change the proportion between 2 sides, it'll change the angles. If you try to grow one of these sides up, it'll mess with an angle. So as long as the angles are locked, then we know the sides are locked into proportionality. You can grow all the sides together, and that will keep all the angles the same. But if we're saying all the angles are the same, like if I have a second triangle over here, try to make it bigger. If I have a second triangle over here and I'm telling you I know all the angles are the same, A, well then I know that this is scaled up. This is a scaled up version of this one. Because the only way to keep these the same is to scale up the sides at the same time all together by K. Let's call it K. A, B, C. This is KA, BA, KB, sorry, and KC. That's AAA works for triangles. Similarity. I mean, if you remember, it does not work for congruency because they can change shapes like that. They can change sizes, but it works for similarity. 2 triangles are similar if they're corresponding angles. We just explained why that's true. Sides will always need to scale together to preserve the angles. Cause all connected. Whereas if we take this parallelogram, we could make the sides long. The sides in the middle could stretch, and the angles could all stay the same. But we had to grow 2 sides together. There's but the angles didn't change, but they're not similar no more. Whereas that's not possible with the triangle because everything's connected. You can't just grow two of the sides. The angles will start to morph at the hinge. Mia thinks the following conjecture is true. She calls it AA similarity for triangles. What do you think? Is it true? Two triangles are similar if they have two pairs of corresponding congruent angles, not three, just AA. Well, yeah, we know that works because if you know two angles in a triangle, you know three. You know all three. Cause add to 180. If you already know two, well then you can figure out what the third one is because they add up to 180. Okay, and lastly, sorry I'm in a hurry. There's a lot going on today. This video's gone on too long already. Using the diagram given in problem 10, how might you modify your proof that triangle ABC is similar to triangle DEF if you're given the following information about the two triangles? Well, this is a side that's proportional. This is a side that's proportional. Let's see. DE, AB, and actually, that looks like it spells a bad word. And if you think about it, this angle is actually in between these. I don't know why they listed the angle first. Here's the proof. We have AB and AC, AB and AC, and we have DE and DF, but D and A are in the middle of both those. So that'll be side angle side. And this one, pair of sides, pair of sides, pair of sides, side, 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 similarity. All three sides are proportional. If all three sides of a triangle are proportional, then because everything's connected, the angles are preserved. So SSS gives you AS, AS, AS. It gives you all, it gives you that these are congruent and these are proportional. Congruent, proportional, congruent. But if you're trying to prove similarity, then this is what you're trying to prove. But if you just know that these are all proportional, then you know this. And that is the side, side, side proportionality theorem of triangles. So let's relate this really quick to congruency. For congruency, triangle congruency, we had ASA, SSS, SAS, and then AAS. For similarity, what proves similarity? SSS proportion, like SAS, and this S's are proportional, and AAA, all angles congruent. It's weird, all angles being congruent proves similarity, but all angles congruent does not prove congruency. Interesting. Wow, wonderful. All right, that's it. On to the homework, or in this case, the homework key.